This is lesson 4.1, completing the square, quadratic formula, and complex numbers. So first up, I'm going to talk about completing the square. One method we can use when solving quadratic equations is completing the square. When completing the square, remember that when we add or subtract a number to one side of the equation, we must also add or subtract that same number to the other side. This is the most important step when using complete the square. So to complete the square, when we have your first term, your second term, your first term and your second term, you're going to take half of the second term and square it and add that to both sides of the equation. So that's written here. This term is half of this coefficient, then squared, and we're putting that on both sides of the equal sign. So here's a simple example of completing the square. We see that our second term is 6, so we'll take half of 6 and we'll square it. So half of 6 is 3, 3 squared is 9. So once we have x squared plus 6x plus 9, we can rewrite this as a perfect square of x plus 3 multiplied by x plus 3. Or x plus 3 squared. Second example, half of this second coefficient is negative 10. Negative 10 divided by 2 squared is negative 5 squared. Negative 5 squared is 25. So we have x squared minus 10x plus 25 factored. We have x minus 5 multiplied by x minus 5, or x minus 5 squared. Next, we'll solve using the quadratic formula. So here's the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a. So your values of a, b, and c are going to follow in this sequence. The first term is a, the second term is b, and the third term is c. So here, a equals 1, b equals negative 6, and c equals 9. So now we can put those in place of the formula. So you have negative b, which is negative 6, plus or minus the square root of b squared of negative 6 squared minus 4 times a times c. We'll divide this over 2 times a. So this negative times a negative is a positive, so we'll have 6 plus or minus the square root. Negative 6 squared is positive 36 minus 4 times 1, which is 4 times 9, minus 36. 2 times 1 on the denominator is just 2. So this equals 6 plus or minus the square root of 0 divided by 2. So the square root of 0 is just 0, so we'll take 6 over 2, which is 3, which equals to x. Okay, for the second example, let's start by writing out our a, b, and c values. So a equals 1, b equals negative 10, and c equals 9. We'll take negative b, which is negative 10. Negative times negative is positive, plus or minus the square root of b squared, negative 10 squared, minus 4ac over 2a. This is equal to 10 plus or minus the square root of 100 minus 4 times 1 is 4 times 9, 36 over 2. (100 minus 36) is 64. So 10 plus or minus the square root of 64 over 2. The square root of 62 is 8. So we can break this up into the positive plus the square root and minus the square root. So this is 18 divided by 2 equals 9. And this is 2 divided by 2, which equals 1. So x equals 9 and x equals 1. Final options. We'll do another example. A equals 1, b equals 4, c equals 2. So from here, we'll use the formula negative b plus or minus the square root of b squared minus 4ac. Since a is 1, we won't be writing it. And over 2, negative 4 plus or minus the square root of 16 minus 8, which is 8 over 2. Now 8 is not a perfect square, but we can factor this out. We have these two groups of 2, so rad 8 equals 2, rad 2. If you need a refresher course on that, there's videos. So next we'll do negative 4 plus or minus 2 rad 2 over 2. These will cancel out. We have negative 2 plus or minus square root of 2, which equals x. Finally, in this last example, we'll set the equation equal to 0 before we get our a, b, and c terms. Subtract 5 on both sides, plus 39. So now a equals 1, b equals negative 16, c equals 39. We have 16 plus or minus 16 squared minus 4 times 39 over 2. 16 plus or minus the square root of 16 squared, 256 minus 156 over 2. We'll have 16 plus the square root of 100 divided by 2 plus or minus equals 16 plus 10 over 2 and 16 minus 10 over 2. So this equals 26 over 2, which equals 13. So x equals 13. This equals 6 over 2, which equals 3. X equals 3. So let's talk about complex numbers next. But first, we'll start with an example of a function with real roots. So this very simple function, f of x is equal to x squared minus 4. You can solve by setting f of x equal to 0. We'll add 4 on both sides to isolate x. We have x equals, or we have 4 equals x squared. Then to isolate x, we'll take the square root of both. So we have x equals 2. So the square root actually will have both the positive and the negative values. So as we set f of x to 0, f of x is the same thing as y on a graph. So when f of x is equal to 0, so here at this point, x equals negative 2 and positive 2 on these points. So those are the roots. So what is the degree of the polynomial? 2, because it goes up to the second degree. And how many real roots does it have? Well, it has this one and this one, so it has 2 roots. So the degree tells us how many roots the function will have. But what do we do when we cannot find that many real roots? When we were trying to solve an equation like x equals the square root of negative 4, we say it has no solution. It turns out that there are 2 solutions. We call these solutions complex or imaginary roots. So we'll solve this one as an example. Set f of x equal to 0. We'll subtract 4 on both sides. And we'll take the square root of it. So we have x equals the square root of negative 4. But we know that we can't take the square root of negative numbers, so we say that there's no solution. And in fact, when f of x is equal to 0, there's nothing here, because this function doesn't cross the x-axis. So complex roots look like this, with a negative square root, in which we notate as I. So now that we know that the square root of negative 1 is equal to I, we can solve some of these equations. So simply, in order to get rid of this power, we'll take the square root of both sides. So the square root of x squared is x. Then now we have the square root of negative 81. So that'll be plus or minus 9i. So this I serves as this negative square root function. $49. We'll subtract on both sides. We'll take the square root. X equals plus or minus 7i. So it's the same as the square root of 49. It's a perfect square broken up into 7 and 7. So square root equals 7, but this time, because there was a negative square root, we'll add I. The last thing to note is that there are 2 special pairs of roots. These are called complex roots that will always come in pairs of 2, and irrational roots that will also always come in pairs of 2. When we find these pairs of roots, the pairs are called conjugates and always look like a plus b rad c for irrational roots and a minus b rad c. Complex roots will look like a plus bi and a minus bi. So this is a complex root, and we notice that a and a stay the same. They don't switch signs. So this will stay negative 5, whereas the second term of bi changes signs. So we'll change this from positive. We'll change it to positive from negative. And this one is an irrational root. And this one does change signs. This one has both irrational and complex components in it, and it will change signs as well. So that's very simple.